Hello students. In this video we'll discuss an iterative method for solving differential equations, which implies that there are existence and uniqueness results for ordinary differential equations of first order. So we're going to consider the following ODE system. Let's consider y prime equals f of t and y, and y of 0 is y0. I would like to solve this initial value problem. A theorem we have is that if partial f partial y, the derivative of this forcing function with respect to the y variable, is continuous, then there is a unique solution to the ODE near, so close enough to y0 and t0. And the method by which we do this is we construct an integral equation. So if we take our ODE and we integrate the ODE, we'll see that if I integrate from 0 to t of dy ds, that will be the integral from 0 to t of f of s, y of s, ds. The fundamental theorem of calculus will now imply that the left-hand side is y of t minus y of 0 will be equal to the integral from 0 to t of f of s, y of s, ds. And so we see that we have an equivalent formulation of our differential equation. So we see that our differential equation is equivalent to solving this integral equation. Y of t is y of 0 plus the integral from 0 to t f of s, y of s, ds. And so this expression over here is our integral equation formulation of the differential equation, which is equivalent to the ODE. Once we have this integral equation formulation of the ODE, we can now construct an iterative sequence. I can define y1 of t to be y0 plus the integral from 0 to t of f of s and y0 of s, where y0 is just what's given to us, ds. y2 of t will be y0 plus the integral from 0 to t of f of s, and then y1 of s ds. And then yn of t will be y0 plus the integral from 0 to t f of s y n minus 1 of s ds. And the sequence yn will converge to the solution of the ODE. The sequence yn of t will converge as n goes to infinity to a function y of t, which is the solution of the ODE. So let's see how this iteration works. So for example, if we had the iteration y prime equals y with y of 0 equals 1, we see that for this situation, this will imply that y of 0 is equal to 1. Y of 1 will be equal to y of 0, which is 1, plus the integral from 0 to t of y when I plug in 1. So I'll just plug in 1 ds. So this will be a 1 plus t. So my first order approximation of the solution of this differential equation will just be 1 plus t. Then y2 of t will be y0, which is 1, plus the integral from 0 to t of the function we found in the previous expression plugged into y. So I'll have a 1 plus s ds, which will give me a 1 plus s squared over 2 from 0 to t. And so we'll see that y2 is 1 plus t squared over 2. And if we continue this procedure, we will see that yn of t is 1 plus t squared over 2 factorial plus t to the n over n factorial. And so this iterative scheme gives me the first n terms in the Taylor series approximation for e to the t. And we can verify that e to the t is the solution to this differential equation, since the derivative of e to the t is e to the t, and e to the 0 is equal to 1. So indeed, for this simple example, we see that this iterative scheme, by plugging in the previous iterations into the integral equation, will tend to the solution as n tends to infinity. Thank you very much.